I came to realize is that since coming to BYU, he's been recognized for every element of being a professor. That he got the Carl Mazur Excellence in Teaching Award in 2013, so clearly recognized for teaching. But he also got the Young Scholar Award a few years ago. He's recognized as a statistician, not here at BYU, but within the society as well. That he got the Distinguished Achievement Medal for the ASA section on statistics in the environment. He's done amazing work addressing a number of important environmental issues, but today we've got him here to talk to us about some of the work that he's done related to climate change. And so to give him maximum time, I'll stop there. But thanks, William, for spending the time with us today.
So is that mic working? Good. All right. Well, thank you for the invitation. I've looked forward to this opportunity, and as I was saying to Rick and Summer up here, it's a little scary too because I can't hide behind my equations as much. I tried to make this a little bit more of a general kind of ideas and thoughts about statistics and perspectives of a statistician on climate change assessment. Kind of a wide variety of things I thought would be interesting to talk about in an interdisciplinary group like this. So here's an outline, and we'll get to some of it. We'll see what parts we get to. But I'm going to start by just talking a little bit about uncertainty and decision-making in the face of uncertainty. Give an analogy that has nothing to do with climate, and then hopefully you'll see the connections. Talk a little bit about the language of uncertainty that's used in the IPCC reports, the Intergovernmental Panel on Climate Change. So they have their own sort of language, and they use words like confidence and likelihood. If you're a card-carrying stat nerd, you'll use those words slightly differently than IPCC would. And so we'll just talk a little bit about that. If you haven't read at least the summary for policymakers, that should be required reading for a group like this that's interested in climate change. If you just Google IPCC summary for policymakers, it's about 28 pages long. Required skimming, at least, let's say that. We'll talk a little bit about this idea that I wanted to talk about, uncertainty and how uncertainty propagates in complex systems, such as human-climate interactions. A little bit about communicating about uncertainty, which is a sticky wicket. And then if we have time, I'll talk about some studies that have been done by I and some colleagues here at BYU, and then some concluding thoughts. So first of all, why are we talking about statistics in a seminar like this about climate change? I'd like to refer to a couple of my favorite definitions of statistics. One that's a little bit more, a little bit of function here. Statistics is the discipline for facilitating sound decision making when you're dealing in situations where there's uncertainty. So this is a natural place to bring in statistics into an interdisciplinary series like this, where we have decisions to make. But my more preferred definition of statistics that we'll be using a bit today as well, especially if we get time for some case studies, is the art of persuading the universe to divulge information about itself. So the more complicated the system, the more difficult it is to extract the signal from the noise. And that's what we're going to try to do with statistical models, extracting that. All right, so just a simple analogy about risk and uncertainty in making decisions. So let's talk about mammograms. So let's suppose you have an abnormal mammogram. What does that mean? Well, first of all, so the National Cancer Institute says that when 1,000 women go in for breast cancer screening for mammography, about 5 in 1,000 will be currently will have breast cancer. So that tells us something about the base rate that people often forget when they look at problems of making decisions and classification about base rates or probabilities. So here's some information also from NCI, and these are rough figures. The sensitivity of a mammogram is 80%. So roughly 80% of cancerous women will be properly identified as having an abnormal mammogram, so about 80%. On the other end, then we can talk about specificity. And this is probably a little too high, but we'll use these nice round numbers for our example. Among healthy women, roughly 95% are deemed normal. So for most of the healthy women, we're properly characterizing them as healthy. For most of the cancerous women, we're properly diagnosing them as having this abnormal mammogram. So the question is, if your mammogram is flagged as abnormal, what's the chance that you have breast cancer? Anybody want to guess? All right, 80% sensitivity, 95% specificity. Seems like we're doing pretty well. Well, let's look at you don't have to follow the calculations here, but we can just walk through just a simple example here. So let's suppose we have 1,000 women. So if we have 1,000 women, 995 are likely healthy, 5 diseased. Among the healthy ones, if we have this 95% sensitivity, then we should have this 945 flagged as normal. Among the diseased, we have this 80% that should be properly diagnosed as abnormal. So we have 4 out of the 5 will be properly diagnosed as diseased. And so if we look at how many people end up with this abnormal mammogram out of 1,000, it's 54. So if we look at the probability that you have cancer given that you have an abnormal mammogram, 7.4%. In fact, that's exactly what's on the NCI website, about 7.4%. This number is called the positive predictive value. So it says that if you have this abnormal mammogram, might not be just time yet to be completely despondent. Most of these women that come out with these abnormal mammograms are, in fact, just fine. If you look at the negative predictive value, that is, if you have a normal mammogram, what's the probability you're healthy? 99.9%. So we have these two probabilities that this one's perhaps a little puzzling that this thing's so low. And we might say, well, what if we want to build a better diagnosis tool, a better system for determining who has cancer and who doesn't? So let's first of all make the problem just a little bit simpler. Of course, if you have an abnormal mammogram, then you go in for a follow-up test, maybe another mammogram, maybe a biopsy. But let's say for now that we only get this one test, this one screening test. And let's also say that the way we're going to make a decision is for any mammogram, we're going to quantify the strength of evidence of cancer from strong down to weak, and then we're going to choose some threshold and say that if the patient has an evidence of cancer that's above this level, we'll classify them as cancerous. Okay? So when we're looking at what's the best way of choosing an action or developing a rule here, what we want to do is alter the rule. Let's say we want to alter the rule so that we have fewer false positives, okay? Because we have most of these women that have an abnormal mammogram are actually they're false positives. Maybe we want to shrink that down. That is, we want to improve these probabilities. So if we want to have fewer false positives, then what we're going to have to do is change this threshold. We're going to move it up so that we have only these people up here are going to be classified as cancerous. Fewer women are going to be classified as cancerous. More of them classified as healthy. Of course, the downside of that is there might be some women who are in fact cancerous that we're now going to classify as healthy. So there's that downside. Well, we could move in the other direction. We could say, well, what if we want fewer false negatives? That is, we don't want these cancerous women erroneously sent home thinking they're healthy. Well, what's the consequence? We're going to have to move the threshold way down, and we're going to see that a lot more women are going to be, who are healthy are going to be classified as cancerous. And there's a cost associated with that, right? It's not free for a woman to go home thinking she might have cancer, right? That's traumatic. That causes some trauma. So what we want to do, if we want to say, well, where's the right threshold for deciding how we're going to move forward, what's our action, what we want to do is we want to specify the relative cost of a false positive and a false negative. You can do this in dollars if you want. You can use just relative numbers, like I think that a false negative is 100 times as bad as a false positive. Okay, that's fine. But we need to think about relative costs of these possible outcomes. And that, along with the base rate, that is 5 in 1,000 women have breast cancer, we could identify a rule that is a threshold or a procedure for making a decision going forward based on valuing these different outcomes, these different costs or benefits. So that's the moral of this analogy. That is, if we can specify possible outcomes along with their probabilities and costs, we can build optimal rules for decision making going forward. And so hopefully you'll see where I'm kind of going with that. That's where we're kind of heading today with modeling climate-human interaction. All right, so a couple of nerdy pieces of business we have to cover. What do we mean by model to move forward with this? So there's a couple of ways in which model is going to be used today, a statistical model and a climate model. So first of all, a statistical model, you don't need to worry about that. Don't write it down. It's just I'm going to draw pictures so I can explain how statisticians use models, what we mean by this. So if I say I'm building a model for sea level, and this is a model for sea level on the eastern U.S., it's joint work with my colleague Candace Barrett and students David Coates and Nate Sandholtz in the Department of Statistics. So we're looking at here, this is for a single sea level monitoring site in Connecticut. The black line is the phenomenon we're measuring. It's just sea level. And here we actually took the data, it's hourly data, but we've averaged over lunar months, because there's a lunar month pattern toward that follows the tides that we can, when we're studying sea level. So these are looking at lunar month averages, and you can see that this thing's going up and down every year. There's some seasonal effects, but this Y is the phenomenon we're interested in. But I'm going to characterize that Y as a linear combination of several pieces here. So I've got a mean, just an overall average sea level for that site. I've got a trend line, because this is what one of the fundamental questions is what's happening to sea level on the East Coast. Globally, sea levels are rising about 1 millimeter a year, but on the east coast of the U.S., it's one of the hot spots for sea level rise. It's about 3 millimeters a year, actually, so really pretty fast sea level rise here. So that's what this trend is doing. And then we've got another piece here that says, well, it's not just a straight line. There's a lot of bumpiness. There's this seasonality within a year. And so this thing is, we call these informally, we call them our M curves, but they're B-splines. It doesn't matter. It's a curve that measures this two bumps that we see every year in sea level. There's one in the late spring, another one in the early fall. And then we've got the last piece is this residual, and there's more modeling going on there. But for now, let's just think of that as the error, okay? So the benefit of using a statistical model for understanding some phenomenon like sea level is we can break it into components, and then we can look at the relative importance of these components. And we can also talk about ways in which we could think about, we can build a sea level measurement by putting these components together. And then we can say things like, is this significant? Well, if the signal here, this change in sea level, is significant relative to the noise, then we can make some sort of decision there. So that's how we use statistical models. The other type of model we're going to talk about today is a climate model. So a climate model, I don't like that we call it a climate model at all. I'd call it a climate simulator, just because I think models should be held sacrosanct, right? That's what statisticians use. But that's okay. We'll use the phrase climate model is good and stuck, so we'll stick with that. And I use that term as well, so that's fine. So a climate model is simply, you can think of it really, whereas a statistical model tries to describe data that you have, a climate model creates data, or it simulates data. So it's a system of mathematical equations that use laws of physics and fluid dynamics and chemistry to simulate interactions of atmosphere and ocean, land, ice. And so what we're looking at here is there's about 35-ish different climate models used by this. This is the Climate Model Intercomparison Project. And you can see that all the models are doing something a little bit different, but they kind of track each other, and they also track, the black line is measured temperatures, the red line is the average of those models. So this is a tool that we can use in the physical sciences to understand potential, basically it's like a laboratory. In fact, statisticians would call this a computer experiment. It's a laboratory where we can say, well, what happens to the climate if we poke it in different ways? What if we remove anthropogenic greenhouse gas emissions? What would happen to climate? Or what would happen to climate if we never had a volcano erupt? Right? We can do experiments. So these are really powerful tools in helping us understand climate in the past and going forward. Important thing to remember about climate models is they are models or simulators of climate, not weather. Okay, so there's a difference there. Statisticians, we have a nice definition. We say climate is the mean and weather is the observation. Or you could say climate is what you expect and weather is what you get. So climate, you could think of as weather averaged over a long period of time, 20 or 30 years typically. So we're not saying that these climate models are going to be able to predict what's going to happen in 2015 or any other year, but we'd say that over a long period of time they should mimic what's happening in climate. And so that's what we're looking at here. This is the multi-model surface temperature. And this nicely matches what we've seen in recent history. In fact, here's our model, the bias. And so if we're doing a reasonably good job, we'd like to have most of our colors here light blue or yellow, and not have a bias that's where all of the colors are red or all of them are blue. And it looks like, in fact, these models, there's a few places where we might miss it a little bit on the high side or on the low side, but for the most part, climate models do a nice job. It's a nice tool in helping us to learn about our climate system. And all of these are from the IPCC report. All right, so let's talk just a little bit more about the IPCC language, because this is helpful if you're going to be educated about how IPCC refers to things. So just a couple of results here, and these are exact quotes from this is the summary for policymakers. A couple of pictures from the summary for policymakers. Exact quote, all I've done is I've added the red font and I've underlined here because these are words that we're going to pay particular attention to here. So here this is looking at each of the last 3 decades has been successfully warmer than any preceding decade since 1850. And this most recent 30 years was likely the warmest 30-year period in 1,400 years. So they say this is likely and medium confidence. So we'll come back and look at those words here in a second. Here's another result. So here we're looking at human-induced changes. So human influence has been detected in warming of the atmosphere and ocean, in changes in the global water cycle, reductions in snow and ice, et cetera. It's extremely likely that human influence has been the dominant cause of observed warming. So again, one of these phrases, they actually do italicize whenever they use one of these terms that's a term of art within IPCC reports. I've just highlighted it red. And you can see here, this is one way in which climate models can be helpful in understanding the human impact on climate change. What we're looking at here is the climate models. If we pull out the anthropogenic forcing, greenhouse gas emissions and such from industrial or auto, whatever, these human impacts on greenhouse gases. If you pull them out, all the climate models are giving us temperature records that should look like in this band. If you put them back in, we get climate simulations that look like in this pink band. And you can see there's the black line is the temperature record. And what we see over and over is that in many, many different phenomena, it's very difficult or impossible to get a climate model to mimic what we've been seeing unless we include those greenhouse gas emissions, those anthropogenic forcings. Here's just a similar picture looking at different kinds of phenomena, different parts of the world, Arctic sea ice, temperatures in North America, Europe, Asia. There's a few places where you don't see dramatic differences, like in the Antarctic here. We're looking at sea ice extent. The models with and without forcing don't show a huge difference here. But for the most part, you're seeing that there does seem to be an impact here on these climate simulations. All right, so what do these words mean that we are seeing? When we talk about confidence, these words are chosen based on the agreement of the evidence on the topic we're talking about and the type or amount or quality, consistency of the evidence. So as the amount of evidence or the quality of the evidence increases, and as the agreement across studies, across scientists increases, they would call this blue area here high confidence, and then medium confidence and low. But you'll notice there's nothing terribly quantitative there. It's a group of experts putting together their best assessment of the confidence associated here. Similarly, we can look at events' likelihood or probability. They use these terms, so we've already seen a couple of them. Extremely likely, we saw very likely. Virtually certain means that the scientists quantify this as a 99% probability of occurring. So when we saw that humans are extremely likely to be influencing these changes we've seen recently, we're saying, the scientists are saying, we think this is a 95 to 100% chance that this is coming from humans. There's several challenges and problems associated with this, most of them identified by the writers of the IPCC report. This is a really hard job to quantify how much uncertainty there is associated with any of these findings. So this is actually a report of some instruction from this committee on how to consistently treat uncertainties. And they identify several challenges, including the difficulty of finding consensus among diverse views. They give instruction on how to avoid this tendency of groups to converge on an overly narrow view, and you'll see that this paper cites the social science and psychology literature quite a bit. It's very well researched, giving good advice to these scientists as they write their reports, these different chapters. Talks about the effect of framing, that if we say something like there's a 10% chance of death versus there's a 90% chance of survival, that these two things will be interpreted differently by humans with complicated brains. There's a lot of emotional baggage associated with the way we interpret some words. So there's instruction there, and there's talk about tendency to underestimate structural uncertainty. That is, we might start arguing about the value of a parameter in a model without realizing that, oh, maybe the whole model could be wrong, right? So we need to recognize that kind of uncertainty. A couple of additional challenges that I would note here is that, as I said before, these aren't fixed quantitative approaches. They're non-statistical approaches to characterizing uncertainty. Ideally, what would we do ideally? Well, I'd use things like Bayesian hierarchical models, or you could use meta-analysis to try to summarize evidence in a quantitative way. Pretty hard to do, though. I mean, this is a massive undertaking. The physical science report cited 9,200 papers. Imagine trying to gather all of that data into a study, right, and try to synthesize that in a big statistical model. So it's hard. I'm not criticizing the IPCC writers, but just saying it would be nice if we could do something better, something more sophisticated. Also, there's a tendency for human judgment to distort the meaning of probabilities, and this is something Kahneman writes about in his book, that when we say we're talking about, say, extremely likely, 95% chance of something happening, well, what does that scientist mean when they say 95%? So this is a table from his book, Thinking Fast and Slow, one of my favorite books that I've read in the last 10 years. So here's some actual probabilities. And Kahneman used games of chance, monetary gambles, to try to understand how humans interpret these probabilities. Are we really good at understanding what it means when something has a 1% chance? Well, in these experiments, they say that even when someone knows intellectually that there's a 1% chance of an event happening, their behavior, in sort of an economic sense, they act like it's a 5% chance. If I tell you something has a 99% chance, you're probably going to act like it has a 91% chance if you're the typical person, right? So when a scientist says 95% or extremely likely, are they talking about this scale, or are they talking about that scale? So these are hard things to do. This is why we like to use formal statistical methods in quantifying uncertainty. It's really hard to do. So again, I'd like to see something better, but I don't know that I could have done anything better given the task. So it's something to work for. All right, so let me talk this is one of the main ideas I wanted to talk about today, is how uncertainties in complex systems can propagate, and these systems are very difficult to work with. So this is a model. This is from a paper by Maslin. It's based on a similar figure in Hillerbrand and Gill's paper, talking about how there's uncertainties or unpredictability that in a complex system, such as human-climate interaction, there's a way in which these uncertainties filter through this whole process. So when I talk about a given scenario that I say, well, I think that emissions are going to go down over the next 80 years, or I think emissions are going to remain just as they are. They're going to go up dramatically. There's going to be different possible outcomes in terms of greenhouse gas concentrations. And what does that mean? Well, every one of those different concentrations that could occur are going to lead to their own sort of suite of possible temperatures, right? Because there's uncertainty there. And every one of those impacts humans in different ways. And so we have biological and demographic models that are going to change dramatically. So as this uncertainty, Maslin calls it a cascading uncertainty, the potential for outcomes at the bottom to be unpredictable increases, right? So we have highly unpredictable outcomes here. It doesn't mean that the problem's intractable or that we shouldn't engage it, but just that we should recognize what we're dealing with when we have these complex systems. What kind of uncertainties? Well, this for example, here's several different climate model runs where we're assuming a fairly optimistic greenhouse gas emission scenario. And you get different answers in terms of its heating potential, different answers in the worst possible case as well. So those are the kinds of uncertainties. Uncertainties that are associated with our assumption about the relationship between CO2 and temperature increases. Those aren't perfectly nailed down. There's some uncertainties there. There's uncertainties associated with the way we characterize these climate models or climate simulators that lead us to have these fairly wide variety of possible answers. So if we take these uncertainties and plug them into a linear sort of system of these interactions, of these models, that's even perhaps too naive, because perhaps our system is actually more of a complex system where there's arrows pointing every which way. So here's a picture from one of these IPCC reports, which I think is nicely characterizes how messy this can get. As climate changes, it impacts things like food security and water resources, which then is going to change socioeconomic development. But then as economies develop and social systems change, well, that's going to affect food security as well. So we've got all these arrows pointing in all these directions. Uncertainty at any one of these relationships is going to propagate through the system. So how are we going to handle this? Well, let's first think about just a nice simple linear system here. A naive view of how we would handle uncertainty in a hierarchical system like this. So let's start with some scenario. I think that emissions are going to keep increasing over the next 80 years. So we're going to start with some point like this. What's that going to mean on greenhouse gas concentrations? Well, we could get any one of these possible answers, let's say. From every one of those, then, I'm going to say, well, I can only want one answer to go into my next model, which is going to take greenhouse gases and turn them into temperatures. So I'm going to take the mean of these guys and plug it into the next model and get the next set of uncertainties. From the temperatures, I'm going to plug those into my health model to look at disease rates and such. So I'm going to take each mean at each level and run my next model. Each model has uncertainty. Take the next mean, move it forward. And at the end of the day, I get some socioeconomic or climate outcomes where I've got this distribution of possible outcomes that's probably way too optimistic. It's probably way too narrow. So what's more likely to be occurring, and what we should probably think about doing as we build these complex systems, is take every one of these outcomes and then say at each one of these possible greenhouse gas scenarios, let's run the climate model and see what happens to temperature on each one of these. Okay, so you can see how, now at this point I got tired of drawing lines and started doing a lot of cutting and pasting. So this is just me just making a picture. It's not real data. So when you look at this in real life, you'd see some of these lines. When we get down to a bad enough scenario, maybe there's going to be a strong upward pressure for different sort of behaviors, or up here maybe there's going to be a stronger downward pressure. But my point is, as you build these systems, you're going to see the possible outcomes. We're going to have a much wider variety of possible outcomes. And that's what we need to characterize when we want to make decisions going forward, is looking at those possible outcomes. This is the set of outcomes that I'm going to look at, comparing back to my breast cancer illustration at the beginning. That was a simple problem because we only had two outcomes. You're cancerous or you're not. Whereas in this scenario, we've got a whole variety of possible outcomes for climate's impact on society. We want to characterize which of those outcomes are most likely. So these out here don't happen very often in our system. These up here happen quite a bit. So we want to characterize the likelihood of each of these. And eventually, we'd like to think about, well, what is the benefit or cost associated with each one of these scenarios? And then we're going to wrap this whole thing around and start over, because this is going to be a continuous loop. So it's a messy problem. All right, just a little bit of a detour here about communicating about uncertainty, because I'm talking about characterizing uncertainty in these systems as if it's what we need to do, and it's so great when you characterize uncertainty and there's no problems. Well, of course, that's not true. I think that what we're doing when we try to properly characterize uncertainty and make decisions in the face of uncertainty, it's what we ought to be doing. It is the hallmark, I think, of good science, is doing proper uncertainty analysis. Things like what things are truly chance, what things are systemic or epistemic uncertainties. But uncertainty is a two-edged sword. We can even though it's the right thing to do, we can get kind of nipped in the rear by being good scientists. Uncertainty for a large proportions of the general public. Uncertainty is equated with sloppiness, or as my teenagers would say, that's really sketchy, right? Really, that looks really sketchy. And often it means if I see uncertainty in any analysis, it means we should wait. Wait until we know for sure what we ought to do, right? So it's often equated with a need for waiting. And then often, if scientific findings are considered to be an attack on or a threat to the way you perceive the world, uncertainty is an opportunity to then attack the science. And we saw this just recently, but we'll come to that in a minute. So here's a memo that I think is telling. It's from a subsidiary of British American Tobacco. And this is how some people, I think, view uncertainty in science. Doubt is our product, says this tobacco executive. Doubt is our product, since it is the best means of competing with the body of fact that exists in the mind of the general public. Can you imagine someone having the audacity to write this down? But they did, so we're glad. This is very helpful. It is also the means of establishing a controversy. Within the business, we recognize that a controversy exists. However, with the general public, the consensus is that cigarettes are in some way harmful to the health. So there are, people that will look for doubt, look for uncertainty, and try to pounce. And so this is a headline from a couple weeks ago. You've all heard about this, that scientists at NOAA and NASA said 2014, the hottest year on record. And in the announcement, so the scientists who made this presentation, Gavin Schmidt and Thomas Carl, they presented this. They talked about, what does this really mean when we say 2014 is the hottest year on record? Well, we can't just take out a thermometer and stick it in the mouth of the Earth and find out what exactly was the temperature last year. It's not quite that simple. We've got a network of measurements spread in different areas, and we have less thermometers sitting around in Antarctica than we do in LA. And so some areas are harder to measure than others. But with all of this data, we can say that really, this is what a scientist would say the temperature was in 2014. They'd draw a curve like this and say, we don't know exactly what the temperature was in 2014, but I can give you a distribution for the possible values because we know there's uncertainties associated with this estimate. And so here's this distribution. This is a tweet from Gavin Schmidt saying, so here's what we think the temperature was in 2014. Before this year, the hottest year on record, I guess, was 2010? And 2005 were also hot years. And you can see these here. So this is actually a history of all of the hottest years on record as we've moved through. And you can see that each year we get something that's a little hotter. One thing I can say, I'm a statistician, you can trust me, among the last 130 years, some year was the hottest. There was a hottest year, I can say that, and you can trust me. We don't know for sure that 2014 was the hottest year. It's certainly the thing to bet on. In fact, that's what this slide was, slide 5 of their press briefing. Slide 5 of the press briefing says 2014, given these uncertainties, we don't have a single number, there's a 48% chance this was the hottest year on record. If you want to bet on 2010, it's a worse bet. You've got an 18% chance, right? That's what we're looking at here. NASA had slightly different numbers. But the scientists did a great job in saying, here's the evidence, here's the uncertainty associated with it, and what was the reward? They were pounced upon by the naysayers. Most dishonest year on record, says thefederalist.com. I love this. As we're about to see, this is a claim that dissolves on contact with actual science. Right? It's very sinister stuff. This is from the Daily Mail. But it emerged that GIS's analysis is subject to a margin of error. Shock. Right? There's error. NASA admits this means it is far from certain that 2014 was a record at all. It shows up. He buried it in slide 5 of his presentation. So it wasn't buried at all. They admit they're fudging the facts. Okay, so this is the kind of thing that can happen to us if we're being good scientists and talking about uncertainty. Lost in this discussion of was this the hottest year or not is this important fact. 2014 was really hot, as were all of the other years in the 21st century. And sadly, it really doesn't matter if 2014 gets the gold medal for hottest year or not. What matters is, are we seeing a change in the climate? And And yes, all of these years since the turn of the century have been really hot years, and we've had no strong El Nino events as well. Once we have another strong El Nino event, you might expect to have a really high temperature. So what's the lesson here? Do I fault the scientists? Not really. Should we be talking about nuance and uncertainty? I think we should. Some people might say, well, science has bad PR because we talk about nuance, we talk about complexity, and we ought to give simple messages. Well, I think that's true to a degree, but it's a hard question. I don't know what the right answer is. You're going to be, it's kind of there's not a silver bullet here. But this is something we need to be ready for if we're going to be doing good science. Instead of going to, I'll go through a blitzkrieg case, some ways in which, well, maybe I'll show one example. So this is work with Summer Rupert and Phil White and Shane Reese. Here we're trying to understand Antarctica's surface mass balance. So accumulation minus ablation at the surface. So what we're saying is what's happening at the surface of Antarctica, not any melting at the base, not calving or chunks of this ice sheet breaking off. Just saying what's happening in terms of this surface. So the motivation here is the total mass balance is going to be key to sea level rise. There's lots and lots of water stored on Antarctica. And if this thing is shrinking dramatically, that's going to have a dramatic effect on sea level rise. So the total ice sheet, it seems to be shrinking in size, and we want to better understand this so we can make decisions going forward. This is one of those uncertainties that we'd like to better nail down. One of the problems is we don't have great data. There's not a lot of people living in Antarctica that can put out thermometers for us or measure rainfall, precipitation. So and some of the data is better than others. The blue data here are points that are A-rated, good data. B and C data are red. And so what we want to do then is build a model for Antarctica totally. What's the total surface mass balance? That is, how much are we gaining each year from precipitation? And then we can compare that with loss. So these are very early estimates, not ready for prime time, but just kind of as a proof of concept, what we were trying to build is this complicated model that uses all of this information as well as geographic data to try to understand what is accumulation looking like and what kind of error is associated with each of these locations. And you can see we have more error around the coast where precipitation is more volatile, big boom and bust of precipitation. And what we're going to try to do then eventually, and again, this is very early, and we don't really trust the error bars yet because we haven't built the final models, but in some early models we're seeing that it looks like accumulation is comparable to other estimates. This is our estimate here, but perhaps a little bit lower. And what we did over here is we said, given the uncertainty associated with quantifying how much ice there is on Antarctica, where would you best gather new data if you wanted to minimize your estimate of the overall uncertainty for Antarctica's surface mass balance? And so we built a set of predictions. We said if you wanted to choose the one best place to shrink the uncertainty about Antarctica, there's the first place you'd go, and there's the next place, and we'll send Summer and her team out here because that's really hard to get to and cold and stuff like that. So these are the kinds of things we're trying to do is build models that account for this kind of uncertainty. Summer will talk about a bunch of other cool things next week, but let's go to some concluding thoughts here and then maybe a moment for questions. So what would I like you to take from today? Statistical modeling is a way of facilitating the decomposition of these complex processes into components that are germane, that we can then make inquiries about this climate change question. And climate change assessment is inherently a statistical problem in the sense that we've got all of these issues like trend detection, multivariate modeling, integration of diverse sources, and statistical models are, in some ways, I think, our only hope of really extracting something that's really actionable. An example, don't worry, you don't have to, we won't be examined on this equation either, but what I'm trying to show here is how a complex statistical model can take data from a variety of sources and help us make decisions. This is a paleoclimate reconstruction by some friends at NCAR. This is the records of temperature during the era where we have thermometers, right? 1850 on. This is what we'd like to get at, is temperatures going way back into the distant past. What we have are these data sets that are connected to temperature but are not perfect. Tree ring data, dendrochronology, pollen data, borehole data. So these things are connected to temperature and should help us to tease out what's going on with that ancient temperature. We've also got some data that tell us about these climate forcings, solar irradiance, volcano behavior, and greenhouse gases. So if we use all of these data together and feed them into a phenomenologically sound statistical model, we have some hope of getting something that's useful and actionable along with measures of uncertainty. And the second point, modeling complex human-climate interactions require interdisciplinary input. Sometimes we say, oh, there's room for everyone, and it's all kumbaya, and it's sort of I don't know, demeaning, or you feel like you're being talked down to. That's not this case. This is really a problem where we need a wide variety of disciplines to work on this complex system. Not only things that wouldn't surprise you, like chemistry and physics, computer science, math, geology, biology, agriculture, engineering, but in this, we also need models in this complex system that use economics, geography and demography, epidemiology, ethics, political science, sociology. All these things are key. And the research groups that are really doing well in trying to approach this problem have a wide variety of people across disciplines working on these problems. I did a site visit for a site that was proposing to get NSF money for doing this kind of things. And they were literally getting people from all of these disciplines, psychologists, sociologists, ethicists, along with all of the hard scientists. And it was really exciting to see science moving in that direction. Another thought on decision makings. So when we come to that problem of how do we best choose an actionable philosophy, how do we choose a rule going forward, I think what we need to recognize is that uncertainty is inevitable when modeling, but if we have, when modeling both the effects of climate change and the effects of our responses to climate change, but if we can build these complex systems that involve everything from chemistry to ethics and sociology, and we take these outcomes and their probabilities, if we can get those probabilities and these costs or utilities associated with each outcome, and then select an action that minimizes the expected cost across all these possible scenarios, or another way you could think of it as maximizing expected utility, I think that's our best hope for trying to solve this problem at a very kind of big picture sense. Is there problems with this? Sure. You could question the morality of this sort of utilitarian approach. Is it okay if what maximizes welfare for the human population throws some geographical regions under the bus, right? Maybe there's some parts of the globe that really dry out and famine and starvation. Well, but the rest of the globe is doing pretty well. So we need to incorporate that. Well, what do we want in terms of ethics and making sure that this is that the actions we choose are fair to all of the stakeholders. We also need to worry about the tendency to discount future generations, treat them like they're not as important as us, or the tendency to ignore people's society's ability to adapt. Those are things that are difficult to build into a decision rule. And then lastly, is all of this worth engaging, right? John McCain a while ago, someone said, you used to be interested in climate change and now you don't do it much. Why? And he said, well, I'm kind of moving on to things where I feel like there's some hope of doing something, right? Whether that's a cop-out or not, I think that's a view that a lot of people have. Well, I think that there is some evidence of progress, maybe, right? So just last week, the source of all great scientific knowledge, the U.S. Senate, had several votes on they're determining for us what is true. Climate change is real and is not a hoax. This was encouraging to me, actually. 98 senators voted yes, 1 voted no. The no was from Mississippi. From Mississippi? Alabama, sorry, folks in the Deep South. It was somewhere down there. So this was climate change is real, not a hoax. Even, what's his name from Oklahoma? James Inhofe. Even James Inhofe voted yes. Of course, then he later said, well, of course climate's changing. I've read the Bible. There's climate change there. Right, so literally, that's literally what he said. So that was the first vote. So another vote. And all of these, you have to kind of take it with a grain of salt because it's sort of, connected to Keystone XL, and so it's complicated. But even so, I think that we can look at these votes and say, well, there's something we can learn here. Here's the next bill. Climate change is real, and human activity contributes to climate change. Actually, it weren't presented in this order, but this one actually got 59 votes. 15 Republicans voted along with 44 Democrats for this one. The last one, climate change is real and human activity significantly contributes to climate change. Actually, I think this one was voted on before that one. I can't remember. But this one, 50 votes. So this is big progress, actually, over the last 10, 15 years. I don't think you'd see anything like this in the US Senate 10 years ago. Do we have a long ways to go? Yeah. Is it embarrassing that we have this many senators that don't recognize the abundance of data for the human impact on climate change? I think so. But I think there's reason to move forward with some optimism, willingness to engage this. John McCain actually said on the same day, I don't think anybody disputes that it's real. The question is what you do about it. And actually, I agree with that statement 100%, right? What are we going to do about it? There is a wide variety of possible actions. Everything from doing absolutely nothing to having huge impacts on society and the way business runs. I think going forward, first of all, we need to separate the scientific questions from the political ones. I think part of the problem is that people think, well, I can't really look at that data because I know what it means in terms of the outcome. If I believe that humans are causing climate change, then it means that I must, and then something bad. Right? Well, that's not necessarily the case. Let's take the scientific questions, the assessment issues, and treat them fairly. And then once we can really treat them fairly and have an environment where we can say, no, you can treat the scientific question different from the political one, and we'll respect different political views, I think we're going to have a lot more potential for hope going forward. So with firm scientific footing, I think we can choose actions wisely using something like an expected utility approach. So that's what I have to say about that. Thanks for listening.